Okay, folks, I just want to briefly talk about the heat capacity of solids and liquids. So you notice that this is a be familiar learning goal. So we're only going to touch on this briefly. So if we first look at the equation for the heat capacity of solids, it's pretty complicated looking at first, but we can actually distill this down to some pretty simple terms. So let's do that. So here we can see CVM as a function of temperature equals 3R times this other function in temperature. And here is a graph of that relationship. And of course, this function f of e of t is a really complicated looking equation that you can see right there. So there's a couple different formulations for this. There's the Debye formulation and the Einstein formulation. As it were, the Debye formulation is just a little bit more accurate at lower temperatures. But as you can see, at higher temperatures, they have good agreement. So the E right there stands for the Einstein formulation. So here's what I want you to note. At large temperatures, you can see this heat capacity approaches 3R. So look at my y-axis here. That's CVM divided by R. So when it approaches this value here, it's getting to that ideal value 3R. So why 3R, and what is that all about? Well, if we think about our solid, and here I'm going to draw a really crude example of a unit cell. So suppose I have just some very simple looking unit cell, right? Well, we know that there are three dimensions in which it could move, X, Y, or Z. And as it turns out, because it's locked into this lattice, these are not translational degrees of freedom. These are vibrational degrees of freedom. So it can vibrate just ever so slightly within the lattice. So it can vibrate out into the X, it can vibrate out into the Y, or it can vibrate out into the Z, each of which would give us a 1/2 RT, 1/2 RT, and 1/2 RT. However, because this is not an isolated atom, like in the gas phase, really far away from its nearest neighbor, motion in the positive X is very likely different than motion in the negative X. And similarly, motion in the positive Y is going to be different than motion in the negative Y, and motion in the positive Z is going to be different than motion in the negative Z. And that's because in a solid lattice, it has nearest neighbors. So as it turns out, this gives us 6 degrees of freedom, each of which being 1/2 RT. So 6 times 1/2 gives us 3 RT for the internal energy, and thus the heat capacity idealized is 3R. So now what's all this stuff, below this certain temperature, okay? Well, if we inspect this function here, I know it looks complicated, but I want you to take note here that this has the form of a partition function. Okay, that's all that I want you to recognize there. So that theta E, that's what we refer to as the Einstein temperature. And if we take a look at the units here, H times nu gives us a unit of joules, right? So H is a joule second. Nu is the frequency of vibration. So that's what that nu stands for, the lattice vibration. So that's got units of 1/seconds. And then, of course, K Boltzmann is joule per Kelvin. So we can see the second cancel, and the joule cancel. And that gives me 1/1/Kelvin, which is Kelvin. And you can see now here it's divided by 2 times the temperature. So really this 2T, right, times Boltzmann constant, that's beta, okay? So this has the spirit of a partition function because at temperatures lower than the Einstein temp, which we can see here on this reduced space graph, right, T divided by theta, that puts us right up here. That's kind of this magic inflection point where now we have enough population of states that the heat capacity of our solid approaches its classical value, 3R. Okay, so there's some pretty cool stat mech going on here with the solid. I don't want you to concern yourselves too much about this equation other than recognizing it's rooted in statistical mechanics, so it's a partition function. And as we go to a high enough temperature, our solid will eventually approach this idealized value of 3R. And so remember, a heat capacity of 3R, you might be thinking, well, that means all solids have the exact same heat capacity, and they more or less do because this is joules per mole, right? If we were to look at the specific heat capacity, they are all different because each solid has a different molar mass. And as it turns out, 3R is this really idealized value, assuming like this perfect lattice. As we know, lattices aren't perfect. They all don't have the exact same structure. So we'll explore some more specific details in the live lecture. But 3R is our idealized value for the heat capacity of a solid at large temperatures. And large temperatures meaning greater than the Einstein temperature. So really, like, this is still less than room temp. So we expect solids at room temp to be approximately 3R. Okay. So now what about the heat capacity of liquids? Well, each liquid is way different, as you might imagine. They don't have this regular lattice structure. Okay. So we kind of have to take the heat capacity of each liquid at its measured value. So if we look at water, so CS for water is 4.184 joule per gram per Kelvin. I can convert that into its CVM value by just multiplying it by the molar mass. So we can say multiplied by 18.01 grams in 1 mole for water. And then now that gives me CVM for water, which is equal to, with 4 sig figs, 75.35 joule per mole per K. Okay, so that is large. I'm going to write that down. That is a large value, right? We just talked about the heat capacity of solids being 3R. So let's just back that up for a second. 3R, right, is roughly 25 joule per mole per K. So R is 8.314, right, times 3 gives us about 25. So what's going on with this large heat capacity? Well, we must infer that it's due to a large number of degrees of freedom. That's where this comes from. So where are we getting all those degrees of freedom? Well, hopefully if you're looking at this picture and thinking about this complicated hydrogen bonding network, you might be thinking to yourself, aha, here are all of those degrees of freedom. So let's reverse engineer this number, and we're going to come up with what our apparent degrees of freedom are. So let's say CVM equals some constant times R, right? With a solid, we determined it to be 3R. With our gases, we determined it to be some fraction based on our number of degrees of freedom. So let's try to reverse engineer that number. So if I plug in 75.35 joule per mole per K, and I divide it by the gas constant, so I get 9.06. So it's not quite an integer, but it's really close to 9. We'll say good enough for the point of this discussion. Close to 9. Okay, so what's the significance of 9? Well, if CVM is approximately 9R, then that means we had to have 18 degrees of freedom, right? There's 1/2 R for each degree of freedom in the heat capacity. So if my molar heat capacity of liquid water, right, just backing up, taking this measured number, 4.184, which recalls also our definition of a calorie, using the molar mass of water, we get 75.35, and dividing it by 8.314, we got damn close to 9. Not exactly 9, but close. And that 9 refers to 18 degrees of freedom. Where does 18 degrees of freedom come from? Well, this is so cool, you guys. And this only works for very, very small molecules. But now if I draw a picture of water, so here's my bent structure, okay? So in the same way, and actually I'm going to draw this bigger just so I can make the point. Okay, so here is my oxygen, and here is hydrogen. So this is like way cartoony, not to scale. All right. So in the same way that we considered all the ways that our solid can move around and vibrate, let's do the same thing for each atom. So the oxygen atom here is, I want to do that in a different color. So the oxygen atom is free to move in the plus or minus x, right? And we established that because this is a condensed medium, there's going to be neighbors very close. So it's not like the gases where all of those dimensions are degenerate. These are all different. So it can move in the plus or minus z, and it can also move in the plus or minus y. So if we imagine fixing the location of those hydrogens and allowing that oxygen to move, we're really just describing molecular vibration, right? Well, each hydrogen can also do the same thing, right? Each hydrogen can move in the plus minus z, the plus minus y, and the plus minus x. And then same with this hydrogen here, 6 degrees of freedom. Maybe you've already arrived at this, right? But 6 DOF per atom, and there's 3 atoms. 6 times 3, you guessed it, 18 degrees of freedom. This is really cool. So it's not exactly this, right? We calculated that the measured value is 9.06, but it's really damn close. This only works with very small molecules. So some of you might be thinking of like a protein that might have thousands of degrees of freedom. So it kind of falls off at a certain point, but works really well with a molecule like water. So this is really cool, I think. Okay, folks, we'll explore more of this in the live lecture. I'll see you then.